Welcome to NPTEL course on Combinatorics. So this is week 12 problem solving session for this course. So let's start. Let me share my screen and start the things. So okay, so let's start. Recall. So just a quick recall what we have done in this week. So what we are doing last week, we are starting with species, right? So what is a species? So species is a rule, or if you are familiar with categorical definitions, then this is a functor. So species is a rule which assigns assigns पहला each finite set U to a finite set Fu, and second one is to each bijection U to V, let's say sigma, of sets a map Fu to Fp, called as F sigma, for which such that following condition hold. What is the conditions? First condition says that f of identity of U means U to U, we have identity map. This should be identity of Fu. And the second one says that if like U to V to W, we have, let's say, this map is a sigma, this map is a tau, then we have correspondingly to then f of, first we go along sigma, then we go along tau. This f of tau o sigma is f tau o f sigma. This thing should hold. So these are the so this is the definition of a species, and then we saw several examples like we last time did this. I'm just recalling. So then what we did, we saw very like species of sets, species of k sets, species of permutation, species of cyclic permutations, cyclic permutation, species of trees, species of linear orders. All this we have done. Then what we have done in last time in week 11 session, we have computed generating function, computed generating function, exponential generating series, and isomorphism type generating series. We have computed last time generating series, exponential generating series, and isomorphism type generating series for our species. And what we did last time, we saw there are various operations on these species. So we saw operations on species, operations on species, like operations of species, like We saw their product, their composition, their differentiation, all these things. So this week we continue. So this week part continue that, like in this week's first lecture, we saw that we define pointing operation called, so another so operation which is like last time we saw many like addition, product, composition, differentiation, all these things we have seen in last time. And then this week we started with pointing. And like for example, in case of species of tree, like we are pointing a vertex, that means that is a rooted tree. Then we define species of labeled trees, labeled trees, like pointing two vertices. So labeled trees, species, uh, labeled trees, like twice pointing. Initial pointed vertex is tail and later pointed vertex is head. And then we saw various, like this species is same as S plus A and all these things. We have done several computations there. So then in second lecture we reviewed whatever done till now, like all these things from start to ending. Then in third lecture of this week we saw that what are the further directions in this area, like linear algebra method, polynomial method, probabilistic method, so on. But in fourth lecture, we again briefly overview this linear algebra method. So in which we start this town club problem. The main, you are in a town. If you are in a town, then people start forming a group. Then, like under several conditions, what are the maximum number of possible such groups? But there is, in this direction, there is a theorem which is known as a odd town theorem, and which has been proved by linear algebra. So that's why linear algebra methods are useful in combinatorics. So what is the odd town theorem? So odd town theorem says that in a city with n people, there cannot be more than n clubs under the rules of odd town. The rules of odd town. So what is the rules of odd town? So rules of odd town. Rules of odd town. So what is the rules of odd town? Odd town rules means the odd town rules means uh, odd town rules means first rule is every club have odd members. Uh, any two club have even number of common members. Clubs have even number of common members. So under this condition, this says that if you put these two conditions, then there can be at most n club. So this is interesting, and this is proved purely by linear algebra method using inner product. We can define first we have followed this proof, I guess, in lecture. So basically, to each club we assign a matrix, basically incidence matrix. Like if some like if some suppose we have n peoples in there in city, so we have n cross 1 matrix, like corresponding, if that person in a club CI, then we put 1 at that place, and if that is not in CI, we put 0 in that place. So in that way we form matrices and then do computations, you define inner product, and then mention write this condition in terms of inner product and then see what we can do. And we have proved that this vector space has dimension n at most, and we have proved that these are n linearly independent vectors. So yeah, so this is the basically idea of the proof of this theorem. So this is Ortown theorem. So, and this is the this we have covered in this week. So this is interesting. We will do some problem in this direction, and then there may be another interesting question, like you can change the condition and then can see what can we say in such situations. So, and what else we have done in this week? We have done Adolph's theorem. What is that? It says that if n choose t is less than equals to n, 2 to the power 1 minus t by 2 is less than 1, then rt is greater than n, where rt is equals rt comma t. Rt comma t denotes the Ramsey number, where R denotes the Ramsey number. Recall that in first week or second we have done this Ramsey number. Ramsey number RMN means like we need in a club we need like m people know, at least m people know each other, and n people don't know each other. In that way, each person know m people and another person does not know n people. Some, like we have computed R33 and all these things we have done initially. So this is Ramsey number. Then what we did, uh okay, anything else we have started that okay, whatever more we will need, we will write that at like if we need something more, like we have done all these things, Hamiltonian power tournament and all these things, orientation. If we need them, we will introduce them while solving problem, but for timing, let's start solving problems. So okay, good. So first problem. Okay, prove that n cross n matrix over integers with all diagonal entries being odd, prove that n cross n matrix over integers with all diagonal entries being odd and other entries must be even must be non-single. All diagonal entries being odd and other entries being even, other entries being even must be non-singular. Okay, so what the problem is saying, prove that n cross n matrix over integers with all diagonal entries being odd and other entries being even must be a non-singular matrix. Okay, so let's see with examples, then we will try to prove. So what is going to happen? Suppose we are in 2 cross 2 case. So let's say this entry is A1, this entry is A2, this entry is A3, this entry is A4. What is going to happen? So determinant is going to be, we are claiming that determinant is non-zero when this A1 and A4 are odd. A1 comma A4 example. A1 comma A4 are odd, right? and A2 and A4 are even. Even. So if this, what is the determinant of A1, A4 minus A2, A3, A2, A1, A4, A2, A3, A2 and A3, A2, A3. Like now, given that A1, A4 are odd, their product is going to be odd, and this is given that the A2, A3 is even, their product is going to be even, right? Right? Correct. Okay. So what is going to happen? So now how will you prove this? Suppose you try to apply induction to prove this. For n equals to 2, this is going to be true. We have proved this. If this is true for, suppose that this is true for n minus 1 and we need to prove for n. So if this is true for n minus 1, so then what is going to happen? So then how you will conclude that? So if this is true for n minus 1, we need to prove it for n. Then uh, so suppose, so this is n cross n. So if we exclude one row and one column, this is n minus 1 cross n minus 1, right? So this is true for n minus 1 cross n minus 1. So each entry, ah, so right. So this determinant will be something non-zero, and we are multiplying with this one, right? Uh, so so this entry being odd, so this entry being odd will multiply with this one determinant of this one, and which will be odd again. Mhm. Okay, let's see. So without, instead of using induction, let's do in this way. But this is more or less clear intuitively, but let's do precisely in another way by using permutation definition. So let's see. So solution. Let's suppose let Aij, this is n cross n matrix. How we are defining this? The defining Aij is odd if I equals to j. This is given, right? And even if I does not equals to j, right? This is given to us. So how we give the determinant of this matrix A? So determinant of A is given by permutation. Sigma belongs to Sn. This is basically definition. A1 pi 1. I am writing sigma, so I should write sigma for permutation. A1 sigma 1. A2 sigma 2. All these possible products, right? En sigma. En sigma n. Right? This is the determinant of A. Now we see that only, or what is odd basically? A11, I think here it should be minus 1 to the power summation. Here should be minus 1 to the power sine of sigma, I guess. Sine of sigma. Yes, whatever. Is this my definition correct? Anyway, so we're exact. So now see that A11, A22, ANN. So this product basically, this product is going to be odd. This is odd, and every other term in summation is even, right? And every other term in summation is even. So it cannot be zero. So the summation cannot be zero. So the summation cannot be zero. This implies M is non-singular, right? Because if you take difference of two even ones, that is going to be even one. So with odd, it cannot be zero. Yeah. So this is going to happen. So M is non-singular. Correct. Yeah. Good. So what we have done? So we have an n cross n matrix with integer entries, and we need to prove that, like, given the condition that its diagonal entries are odd and other entries are even, we have to prove that this is non-singular. So we use this permutation definition, which says that determinant is like summation taken over all permutation sigma in Sn minus 1 to the power sine of sigma, a1 sigma 1, a2 sigma 2, all these things. Then we see that this is this monomial in this product, in this summation, a monomial only, this only odd term, like there is only one odd term basically when the permutation is the identity permutation. Everywhere else this is even, this product, because as the matrix is defined in this way. So but we see that like odd plus odd plus even, or odd minus even, like this cannot be zero. So the matrix is going to be non-singular. So yeah, that's good. Let's go to next problem. Okay, show that there is a tournament on n vertices that contains so that there is a tournament on n vertices that contains at least n factorial by 2 to the power n minus 1 Hamiltonian paths. Okay, Hamiltonian paths. So what is the problem asking? So the problem is asking that there is a tournament on n vertices that contains at least n factorial. Factorial notation. Mm. That contains n factorial by 2 to the power n minus 1 Hamiltonian path. So we need to know some terms here. So what is first one? This Hamiltonian paths. What is tournament, and every other terms we know, right? So we have to know these terms. So let's define them. So so definition, definition. So what is the orientation? First we need to define that. What is the oriented graph? Oriented graph. Uh, So an orientation of simple graph Z is obtained by giving orientation to each edge of G, each to each edge of G, thus making a directed graph. Thus making it directed graph. Huh. So like examples. So so we suppose we have three vertices. So on three vertices, this is a, let's say this is the graph, then we can give it a orientation like this. Suppose we have this graph, this graph, this graph, this graph, then we can give it a orientation like this. Anything else. So this is obtained by giving orientation to each edge of G, so making a directed graph. Yeah. So this is an example for this. And what are okay, we need to know tournament. So what is a tournament? So tournament, a tournament on n vertices is an orientation of the complete graph Kn, of the complete graph Kn. So a tournament like a, a tournament on n vertices is then orientation of a complete graph Kn. So example like A is the example of this, but B is not complete. So we cannot give B as example. So let's give another example for this. So let's suppose we have, this is the vertices. So we connect them. So this is another examples of tournament. A tournament on n vertices and orientation of the complete graph Kn. And next, what we need? We need definition of Hamiltonian path, right? So what is a Hamiltonian path? Hamiltonian path. Okay. So Hamiltonian path in a graph, say G, is a path involving involving involving, I write incorrectly, involving all vertices of the graph, all the vertices of the graph of the graph G. So, and what is the directed Hamiltonian? A directed Hamiltonian path in G is a path, a directed Hamiltonian path is a path such that all vertices is a Hamiltonian path. A directed Hamiltonian path is a Hamiltonian path. A Hamiltonian, what I'm writing, a directed Hamiltonian path um, is a Hamiltonian path in a directed graph. Hamil is a Hamiltonian path in a directed graph, right? So then we saw a theorem in this direction, like every tournament Tn has a directed Hamiltonian path. This all we have done in lecture. So let's go back, like let's go to our problem. So there is a tournament. So complete oriented graph on n vertices. That is what tournament is, and contains at least n factorial by 2 to the power n minus 1 Hamiltonian path. Huh. Now, so we have n vertices, and we have to show that there is a tournament. So tournament means complete uh, oriented graph on n vertices. There is a complete oriented graph on n vertices that contain at least n factorial by 2n minus 1 Hamiltonian paths, right? This is what we need to prove. Good. So proof. Okay, how to approach such things? Solution. Yeah, proof. At least we have to prove that this much Hamiltonian paths. So in a complete graph. So suppose this is suppose this is our n equals to 3, and this is our graph, complete graph, and we are giving it a orientation. There is a tournament on n vertices that contains at least n factorial by 3 factorial by 2 to the power 3 minus 1 2, that is 4. So this is 6 by 4, that is equals to 3 by 2. So that is equals to 1.5. So there exists, so what we have to show, there exists at least, we have to show uh, there are at least two Hamiltonian paths on this. So what are two Hamiltonian paths? So there are many. So one Hamiltonian path is this one. Another one is going along this and this one. So there are many Hamiltonian paths. But at least what we need to do, we have done that. But now how to prove this? This is basically an example where we are trying to see what is the problem is saying. So problem is saying that if there is a tournament on n vertices, so there is at least n factorial by 2 to the power n minus 1 Hamiltonian paths there. There can be more than that, but at least there are this many. So how to prove? Okay. So suppose, okay, let me write. And so given a tournament T on n vertices, n vertices, n vertices. Now, like keep in mind your this three case, like at that which we have already seen. N vertices, n equals to 3, you can assume. So given a tournament T on n vertices, a permutation sigma in Sn gives a Hamiltonian path if sigma I, comma sigma I plus 1 is in T, right? This is the thing. Suppose, keep in mind this thing. So, this triangle case. Suppose we have this thing. Let's name this. This is 1, this is 2, this is 3, and this is your this tournament T. So now, if you take the permutation sigma is equals to 2, let's say 1 2 3, then what will happen? What will happen is that this will, suppose there is a Hamiltonian path. Let's say this is like 1 goes to 2 goes to, like 1 goes to 2 goes to 3 is a Hamiltonian path. Now, suppose I am taking a permutation 1 2 3. So then what will happen to this Hamiltonian path? So this Hamiltonian path will be like 2, like this Hamiltonian path will be under this one. It's 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this Hamiltonian path will be translated to this one, but this is again Hamiltonian. But this one goes to Hamiltonian, right? But suppose I take this permutation, 1 goes to 3 goes to, and 2 is stable. Suppose I take this one. So then what will happen where this Hamiltonian path go? So 1 will go to 3 and 2 will go to 2 and 3 will go to 1. So this path should be this 3 to 1, but there is no such Hamiltonian path this in T, right? So this Hamiltonian path is not possible. So this Hamiltonian path is not there in T, not there in tournament T. So actually, what is happening? So basically, what I want to give you intuition is that this sigma I plus one should be in T. Basically, I to I plus one is in T. Why this is not there why this permutation is not giving you a Hamiltonian path? Because this 1 3 is not in T basically, right? This is 3 1. This is 3 1. This is not 1 3. So yeah. So what I'm saying to you is that what I'm saying this one claim I am explaining to you. This one, a permutation sigma belong to you gives a Hamiltonian path if sigma I comma sigma I plus one is in T. Like in this case, the like uh, sigma 2 is 3, sigma what is this? In this case, sigma 1 is 3 and sigma 3 is 1. But like sigma 1 is 3 and sigma 2 is 2, but sigma I comma sigma I plus 1, like 3 to 2, this path is not in T. This path is not in T. So that's why this. So basically, what I'm saying that so if sigma I comma sigma I plus 1, okay. So let me go here. So what I'm saying is that you started with a Hamiltonian path, then you are saying that we are trying to produce another Hamiltonian path h dash by a permutation sigma if sigma I comma sigma I plus 1 belongs to T. Like we are naming I plus 1, these are our vertices, n vertices belong to T for all 1 less than equals to I less than n. This thing, right? This is correct. Basically, if like 1 will go to some other vertex, 2 will, 2 I and j, I does not equals to j cannot be go to same vertex, right? Because these are permutations. Sigma is a permutation, so this will go to different vertices. So we have all n vertices covered, so all vertices are covered, and we have a path in T because this is belongs to T. So this is ensuring that this is an Hamiltonian path, right? So what is do I need to write? I guess it is clear. Since so what I am trying to say is that, so this one claim a permutation sigma belongs to a gives a Hamiltonian path if sigma is easy to observe because like uh, so what I should say, this is easy to say, right? I have already said so I don't need to write, I guess. Yeah, I have already explained what is happening. So now let x sigma be the indicator variable for sigma being a Hamiltonian path, right? And x be the random variable for number of Hamiltonian paths, and x be the random variable x be the random variable for sigma being a Hamiltonian path, right? But I'm saying x be the random variable. What I'm saying is x be the random variable for number of Hamiltonian paths, right? Now clearly x, by definition, x is summation sigma belongs to Sn x sigma, right? Now what is the probability of x sigma? Equals to 1. S sigma is the indicator variable for sigma being Hamiltonian path, right? So for sigma being Hamiltonian path, sigma is Hamiltonian path. We have seen that sigma is comma sigma I plus 1 should be in T, right? So there are two possibilities. So how many tuples we have? Sigma 1, sigma 2. In this way, how many tuples we have? Sigma 2, sigma 3, so on, so on, so on. Sigma n minus 1, comma sigma n, right? We have this many tuples. So we have n minus 1 tuple. At each point, to this have Hamiltonian path. So at each point, each sigma I comma sigma I plus 1 should be in T for this to be Hamiltonian path, right? So this is what we have seen for all I, 1 less than I less than n. So this should be in T, but this can be in T or this cannot be in T. So there are two possibilities. So probability for this one is 1 by 2. Similarly, for this to be in T, the probability is 1 by 2. For this to be in T, the probability is again 1 by 2. For this to be in T, the probability is again 1 by 2. So probability is basically 1 by 2 to the power n minus 1, right? P of x sigma. So so thus, so we have, what is the expectation of the random variable x is summation sigma belongs to Sn expectation of x sigma, because we have seen that x is summation of x sigma, and we know this expectation is linear. Since expectation is linear, we have to write since expectation is linear. So that means what is expectation of x sigma? So x sigma is 1 over 2 to the power n minus 1 plus 1 over 2 to the power n minus 1 plus so on, so on, so on, plus 1 over 2 to the power n minus 1. How many times? N factorial times. So this is basically n factorial by 2 to the power n minus 1. Yes. So thus, so this concludes that hence there is a tournament on n vertices that contains at least this many paths, right? We have proved n factorial by 2 to the power n minus 1 paths. So we are done. Yeah. Huh. So next one. So this is clear now. So this problem is saying that if we have a tournament on n vertices, so this contains at least n factorial by 2 to the power n minus 1 many Hamiltonian paths. So we have proved this by probabilistic methods. Yeah. So now next problem. For fixed k, find the exponential generating function shall generating function of Stirling number of second kind number of second kind I, that is, for fixed k, find the exponential generating function of Stirling number of second kind, n equals to k to infinity Sn k x to the power n by n factorial. This is we need to find out, right? So what is the Stirling number of second kind? So number of ways of partitioning n set to k subsets, k non-empty subsets, right? So this is a Stirling number. Uh, we have seen this in lectures, right? So Snk is number of ways of partitioning n set to k non-empty subsets, right? Equivalently, surjections from n set to k set. Uh, yes, that should be because is 0.5 will be, yeah, correct. So solution. So we have to find the exponential generating function for the Stirling number of second kind. So k is fixed. Okay. Suppose uh, 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 solution like this one. Suppose Sk be the species of onto function denote the species of onto function from n set to k set. Onto functions from n to k set, that will like, right. Sorry, I said you is above that. This is same as onto function, but not same as like uh something large. Like you can exchange these two blocks, right? Interchange these two blocks. That will give you different functions, but they will give you same partitions, right? This thing is slightly larger. Suppose okay, I feel that. Okay, okay, so I hope this is clear. So what is saying that suppose you have 1 2 3 4 5 and you are like you are interested Sn2 S52, so that means suppose you have taken 1 2, so like if you are giving a function like 1 2 3 going to 1 4 5 going to 2, this is f function. So f function is sending 1 2 3 to 1 and 4 5 to 2. Now if you take another function, so this is basically partitioning this into two blocks 1 2 3 and 4 5. But like if you take another function, let's say 1 2 3 4 5 to 1 2, by sending these to 1 2 3 to 2 and 4 5 to 1, right? So they will again give you same partitioning, right? So number of functions are more. That's what I'm trying to say. Yeah. So what I'm saying, so sk denote the species of onto function from n to k. Okay. Let e plus denote the species of sets, non-empty sets. So we have computed last time, right? So what is the generating function of e plus? Generating function of e plus. What is that for, like, uh, so you cannot take empty set. So when and cardinality is one, number of sets of cardinality one, that is precisely one. Then number of so what is that, 1 dot x to the power 1. Then if how many subsets of non-empty sets of cardinality 2, that is 1 dot x square by 2 factorial plus so on so on so on. So that is precisely e to the power x minus 1, right? Yes. So this is generating function of this one. So now see that sk can be expressed as e plus dot e plus k product, right? K product, right? Number of non-empty, sk is basically species of onto functions, right? So if suppose skn number onto function from k to n, this is basically epsilon k product of this one, right? This by definition only. So so that means the generating function of this sk is the product of the generating function that we have proved earlier, because if we like a species f is a product of g and h, that the generating function of the species f is a generating product of generating function of g and h. So now, right? So what I have said. So the generating function skx is the product of the generating functions, the generating functions of this species of non-empty sets. Now we have seen already that since since number of number of onto function from n set to k set is k factorial. Since as I mentioned above, we can interchange them. This is precisely permuting them. So k factorial times snk. So what is this series? Summation k equals to n equals to k to infinity snk x to the power n by n factorial What is this thing? So this thing is S and K. We can write 1 by K factorial SK, right? So summation n equals to K to infinity 1 by what is this number of onto function from n to K is, that is K factorial S and K, right? So number of onto function. So SK by K factorial, right? So SNK is SK by K factorial. So SK by K factorial. And inside SK x to the power n by. So this is basically, yes, this is correct. So this is by this one, how to write number of onto function SKN. This is basically uh, SKN is equals to this thing. So this is, so this is SKN by K factorial x to the power n by n factorial. So this is summation 1 by K factorial, you can take outside, n running from K to infinity SKN x to the power n by n factorial. And this we have already seen. What is this series? Uh, this is e to the power x minus 1, right? Yeah. So this is done. That is what we need to compute, right? Good. So we have computed the generative function for the Stirling number of second time. Good. Okay. Okay. Let's go ahead. Question. Any graph with m edges contains a bipartite subgraph any graph with m edges contains a bipartite subgraph with at least m by 2 edges. So we already know bipartite graph. So basically, two parts or subparts of this graph where there is no edge between these two subparts. So we have to prove that any graph with m edges contains a bipartite subgraph with at least m by 2 edges. Okay. Suppose G is our given graph. Let G equals to V comma E, V given graph. and we have to show that it has a bipartite subgraph with at least m by 2 edges. Okay, so we will again prove this by probabilistic method. So let's choose a random subset T subset of V by inserting every vertex randomly with the probability of, like every vertex can either be in T or it may not be T. Basically, the choosing of the subset is very random. By inserting every vertex into T independently with the probability half. For a given age E, so like what is the indicator variable? So for a given age E between U and V, let XE denote the indicator variable of the event that exactly one of the variable of E is in T. Exactly one of the vertices. Exactly one of the vertices of E is in T. Right? Then we know then what is expectation of XE. This is basically either U is in T and V not in T, or U does not in T and V is in T, right? So this is basically probability of U is in T and V does not in T, does not in T, or or U does not in T and V is in T, right? Because exactly one of them should be in T. So this is basically probability of having U in T 1 by T 2, and probability of having T and V not in T is again 1 by 2, plus probability of U having not in T is 1 by 2, and this is again 1 by 2. So this is basically 1 by 4 plus 1 by 4, that is 2 by 4, that is 1 by 2, right? So if X denotes the number of ages, the number of ages having exactly one vertex in T, then basically X is summation E belongs to E, XE, and since expectation is linear, so EX is summation E belongs to E, expectation of XE, and this is 1 by 2, 1 by 2 for each edge, 1 by 2 plus 1 by 2 plus 1 by 2 m times. So this is m by 2, right? So and that's what we need to prove. Like this is same thing as a second one, right? Which we have done. So there are at least m by 2 edges, right? Thus, for some t contained in B, there are at least this many edges crossing between t and v minus t, forming a forming a bipartite graph. So we are done. Graph. So we are done. Okay. So how many participants we have now? Okay, no one. So let's wait for 5 minutes if someone will join. Otherwise, we will stop.